Sure.
Okay, and so welcome to Karol Szumilo from the University of Leeds, who will be talking about infinity-groupoids in lextensive categories. So you're welcome to start, Karol.
Thank you very much. Thank you for the invitation. It's a real pleasure to speak here at this seminar. So as you can see, my title is Infinity-groupoids in lextensive categories. And before I start explaining the words in the title and the actual content of the work that I will be presenting, let me start by going back to the historical motivations and historical background behind this, because everything here starts with this classical theorem of Quillen on the standard model structure on simplicial sets, what we call the Quillen model structure, which he introduced right at the same time when he introduced model categories in the first place. So I'm operating under the assumption that you are more or less familiar with that. The category of simplicial sets has a proper Cartesian model structure with weak homotopy equivalences, confibrations, and monomorphisms as the three classes of maps. This is a standard foundational tool for homotopy theory, which is used all over the place. And our motivation here, and the question that we are asking is it possible to internalize this theorem in categories more general than category sets? So we would like to take simplicial objects in some category E, and this notation SE is what we use for simplicial objects, and somehow write down a general construction of a model structure in some wide class of categories that would generalize this Quillen model structure in some natural way. Obviously, one could imagine some trivial ways of answering the question as posed, but we want to do something that says something interesting about homotopy theory of objects in SE. And so this is the question that I will answer in the rest of the talk. But first, let me say that this was most directly motivated by the following theorem, which is essentially the same theorem as the one from the slide before, but this time it is done in constructive logic and constructive Zermelo-Fraenkel set theory. So it turns out that one can construct this Quillen model structure also constructively, meaning not using any axiom of choice and not using the law of excluded middle. And the theorem looks as follows. We have a proper Cartesian model structure on the category of simplicial sets with Rook equivalences, confibrations, and so-called really decidable inclusions instead of monomorphisms. So this is something that's going to be elaborated a little bit later on. And the talk is going to be really much more categorical. It's going to be much more about category theory than it is about logic. So I'm not going to dwell on this too much. But let me just say that what's happening here is that when you are moving to a weaker logic, like from classical to constructive logic, we have fewer axioms, fewer logical principles at our disposal. So fewer things are provable. In particular, we might be used to looking at certain definitions and being used to the fact that there are a number of equivalent ways of stating certain definition. These equivalences may cease to be true after we work in a weaker logic. So in particular, really decidable inclusion, whatever it is, under the law of excluded middle, it's a monomorphism. It's just a different name for a monomorphism. But when we go to constructive logic, it turns out that there are different ways of saying what a monomorphism is, which are no longer equivalent. And when you are phrasing a theorem like that, you have to carefully pick which one of those you are going to choose. And these really decidable inclusions were going to be explained slightly a little later. It turns out to be the notion that we were able to prove a theorem under. But as I said, the talk is going to be really categorical, so we are not going to be thinking about constructive logic. Rather, we are going to be thinking about these categories E, which in particular include all toposes, Grothendieck toposes. So we can just think about those categories as models of those theories, rather than thinking about the logic directly. So let me just say the theorem here was well, it was first proven by Simon Henry, just 2 years ago already, and then Nicola Gambino, Christian Satter, and myself, we provided 2 different proofs of this theorem in addition to Simon's proof. So we had like 3 different proofs in the mix, and all the work that we are doing, that I'm going to talk about today, is joined between all 4 of us that are listed on the screen right now. We have joined to carry out some follow-up to both these papers, where we take the theorem as stated here and trying to internalize it into some wide class of categories, and that's what the focus is going to be here. So let me go forward and state the theorem, the actual theorem that's the topic of today's talk. And this says that if E is a countably extensive category, then the category of simplicial objects in E carries a proper Cartesian model structure, which we call the effective model structure, which has as its classes weak homotopy equivalences, confibrations, and really complemented inclusions. And the vast majority of my talk is going to be really about unraveling the statement of the theorem and explaining what it means exactly. And then towards the end, I will say something about the properties of this category and the associated infinity category. So, so first, let me just point out 2 things here. We have countably extensive categories as our setup. I'm going to provide a precise definition and some examples in a moment. And let me just point out that for cofibrations, I wrote really complemented inclusions as opposed to really decidable inclusions from the previous slide. If it's the same thing, we have just chosen to change terminology, hoping that maybe the word complemented is a little less intimidating to non-logicians as opposed to decidable. But it's the same thing, and I will explain exactly what it means as well. Okay, so that's our new paper, which we have just recently posted on arXiv. Of course, if you would like to take a look, any comments and feedback are very welcome. All right, so having said that, I'm going to start defining the notions and unraveling the meaning of theorem. And I will be going fairly fast through this and not spending too much time on the details. So I'm certainly assuming some familiarity with various topics in category theory and simplicial homotopy theory and things like that. But if anything needs clarification at any point, of course, feel free to ask. So having said that, let's start unfolding the definitions. So a category is countably extensive if it has finite limits and it has countable coproducts which are all Van Kampen. And that's something that I'm going to also define precisely in the next slide. Before I move on, let me just make a slight comment that both names lextensive and extensive without an L in front of this are in use. And I think the standard distinction is that extensive without L in front does not require all finite limits to exist, only those limits that are needed to make sense of these countable coproducts. And we definitely need finite limits in this context. So everything here is extensive. I may accidentally slip up and use the word extensive at some point, but if I do, it's just by mistake because we were kind of not completely decided which word we want to use. But even if I say extensive, I actually mean that I have all finite limits. So just wanted to get this out of the way. And similarly, I might say decidable instead of complemented. It's all the same for the purpose of the story. Okay, so now let's unravel the definition of Van Kampen colimit. And even though in the definition of extensive category just on the previous slide, I talked only about Van Kampen coproducts, we actually need to think about more general colimits. So I will state this definition in full generality. So let's say that I have a category with finite limits, and say that I have a diagram in that category indexed over some indexing category D. So such a diagram is universal. Or maybe the colimit of this diagram is universal if it is stable under pullback. So if I map from X to the colimit of my diagram via some map, and I pull back the entire diagram, then I'm going to obtain the colimit again. If it is called effective, if a kind of dual property holds or complementary property holds, in that if I have a Cartesian transformation over my diagram, which is so y has an effective colimit if any Cartesian transformation over x satisfies the property that the colimit of x exists as well, and all the squares connecting components of my natural transformation with the map induced on the colimits are pullback squares. So if you think about natural transformations from x to y, and natural transformations between the colimit cones, which involves one extra object, but what I'm saying is that a Cartesian transformation between diagrams extends to a Cartesian transformation in cones. And in this definition, what's important, and maybe it's not always made explicit in these sort of definitions, because typically such a definition would be made under the assumption that perhaps we have all colimits of some shape. Here, I a priori do not assume that we have any colimits globally. I'm just assuming locally that my diagram Y has a colimit. And then part of effectiveness is that any Cartesian diagram over Y also has a colimit. So this assumption has to be built into the definition under our weak assumptions. And then it's von Kampen, a colimit is von Kampen if it is both universal and effective. So this, what it morally means is that if we think about these maps from X to Y as some sort of families, where sort of fibers of each map are some sort of objects parameterized by the base object, then we are saying that these families are kind of glued together nicely along those colimits, and maybe those colimits that they glue over nicely, this is what we are calling von Kampen colimits. And in particular for coproducts, which is what's important in our setup, this is quite easy to understand. If we have finite limits and countable coproducts, then countable extensive means the same, that all countable coproducts are universal and disjoint. Where universal means exactly what was defined up there, and disjoint is what you think it is. If I have a coproduct, then I'm going to call it disjoint if whenever I take pairwise pullback of two distinct factors in my coproduct, then I obtain an initial object, i.e. the pairwise intersections are empty, so to speak. So that's what a von Kampen colimit is, and I realize that this is a very technical notion. I'm not going to delve that deep into how it really works, but if you were familiar with it already, you will be able to recognize how it works. Okay. So with that we know what a countably extensive category is. It is a category with finite limits and countable coproducts, so that families inside this category glue nicely over those countable coproducts. And with that, we're going to describe this model structure on simplicial objects in such a category E. But before, let me point out some examples of these extensive categories. So all Prishev categories are completely extensive, and by completely here I mean that not just countable coproducts are von Kampen, but all small coproducts are von Kampen. A lot of examples fall into this broader category, but or into this smaller category, but we only need countability in our setup. In fact, all Grothendieck toposes are completely extensive, and indeed, Giro's theorem characterizes Grothendieck toposes in terms of these von Kampen colimits. Namely, a Grothendieck topos is exactly a category which is locally presentable, in which both small coproducts and also quotients by equivalence relations are von Kampen. And I think what's notable in our context is that we can get away with having no quotients whatsoever in our category. And indeed, when we started working on this project, we first looked at Grothendieck toposes because we assumed that this is more or less the right context to carry this out. But as we were working on it and started unraveling certain arguments, it turned out that we can get away with fewer assumptions. And in fact, what we need is countably extensive, which at first was kind of surprising to us. But by now I sort of got used to this idea, but at first this seems like really weak assumptions. Okay, some other examples. The category of topological spaces is completely extensive. The category of schemes is completely extensive. The category of affine schemes is only finitely extensive. So it has well-behaved finite coproducts, but not infinite coproducts. So in this case, our theory does not apply. The category of countable sets is countably extensive. And then one thing that will come up late in the talk, if I have time to get to this, the free kappa coproduct completion of a finitely complete category is kappally extensive. So you just sort of formally adjoin kappa small coproducts to a finitely complete category by forming so-called category families, where an object is basically a family of objects of the original category indexed by some kappa small set. And there are fairly obvious morphisms to describe that. But enough to be helpful later on in investigating some of the properties of this model structure which we construct here. So this is a fairly broad zoo of examples. One example that, one thing that is a near non-example is a category of manifolds, which is extensive but not lextensive. It fails to have finite limits, and unfortunately, this rules this category out from our considerations. We really do need finite limits. Okay, then. So let's start talking about clarifying the rest of the statement of the theorem, because so far I explained the hypothesis on our category. Now I need to explain what the remaining things in the statement of the theorem mean. So in particular, let's talk about complemented inclusions. So complemented inclusions are nothing but coproduct inclusions. So the way I say it is that a map from A to B is complemented if it has a complement. So there is another object. So that together, when I take B, so there's another object C called the complement, that when I take the coproduct of A and C, I get B along the specified maps here. So that goes back to this logical thing with decidable inclusions, where we're kind of saying that the law of excluded middle holds for the statement X belongs to A. But I'm going to speak about this purely categorically, so just think about those as coproduct inclusions. And then here's a lemma, which is like the first step to explaining why we can get away with these apparently very weak assumptions, namely, in a countably extensive category, there are some more colimits than those that we have assumed. Namely, pushouts along complemented inclusions exist, and colimits of sequences of complemented inclusions exist as well. And all those colimits also happen to be Van Kampen. Whenever I say sequence, I always mean countable sequence indexed by omega. We're never going to do anything transfinite here. So, and this lemma is less interesting than it seems at the very first glance, because what we are saying is that these colimits, in a very trivial way, reduce to coproducts. Namely, I have very quickly wrote down the formulas for this. If I take a pushout along the complemented inclusion, but this pushout can be computed as a coproduct again. Namely, I take the complement and I attach it to the object that I was pushing into. And similarly, if I have a colimit of a sequence of complemented inclusions, then I'm adding one extra object at a time, and this ends up being simply the coproduct of all of them. So this is a very trivial lemma. But I'm writing this down to point out that this lemma has an interesting consequence when we move to categories of diagrams, which is not as trivial. Namely, in the categories of diagrams, and some parts of this works in arbitrary categories of diagrams, but I'm going to go just to simplicial objects right away. So diagrams indexed over delta op. In this category, we're going to consider level-wise complemented inclusions. So such morphisms that at each level we have a complemented inclusion. So this is a much weaker notion than a complemented inclusion because I'm not requiring that the complement exists as a simplicial object. I'm only requiring that complements exist individually at each level, but they do not necessarily assemble into a simplicial object. So this is now a wider class of maps than level-wise than just complemented inclusions. But the lemma from the previous slide lifts to this just sort of level-wise. And now we can say that pushouts along level-wise complemented inclusions exist, and colimits of sequences of level-wise complemented inclusions exist, and they are from Kampen as well. This means that now in the category of simplicial objects, we have quite a few colimits available at our disposal beyond just the coproducts that we have started with. And this is like a crucial observation that makes things work, in that, of course, in order to talk reasonably about model categories, you need to have at least some colimits at your disposal. Coproducts are really not enough to make sense of a model structure. And this is where these colimits come from. We have at least some pushouts and at least some sequential colimits. This is enough to form pushouts of cofibrations and pushouts of sequential colimits of cofibrations, which is really the bare minimum that you need in terms of colimits to make sense of a model structure. Let me actually skip this remark. That's not super important. Okay, so having cleared out these things about complemented inclusions, which will be coming back over and over again, let's finish explaining the statement of the theorem, namely what this model structure is exactly, how is it constructed. So if we have any countable set, then we can consider sort of corresponding discrete object in the category E, namely the coproduct of terminal objects indexed over this set S. So this is like, you can imagine that there's a forgetful functor from E to the category of sets, which is just sort of homing out of the terminal object. And what I'm saying is, because we have countable coproducts, this has a partial left adjunct defined on countable sets. I mean, we cannot form larger coproducts, but we can form these countable coproducts. So these things of the form as underlined are sort of discrete things inside of our category. And what we are going to do is we are going to take the same generators that we use to construct the classical calculus model structure on simplicial sets, namely the boundary inclusions and the horn inclusions, and we are going to push them into the category of simplicial objects in E via this discrete functor. So we have these boundaries and horns as discrete objects in our category. And we would like to run some version of a small object argument here. But we are going to need an E-enriched version of this argument. Well, because, I mean, the idea here is somehow coming back to maybe to this logic. We are trying to internalize some constructive theorem, thinking about E as being a model of some sort of constructive logic, perhaps. And so we want to think about objects of E as our interpretation of sets in a way. So the appropriate way to handle this would be to say that we are somehow thinking about the E-enriched version of this. However, there is a problem with that, because we have put so few assumptions in our category E. We have not assumed, for example, that it is Cartesian closed. And if we have not assumed that it is Cartesian closed, then the category of simplicial objects is not going to have enrichment, because in order to construct E-valued home objects, then I would need to start with this Cartesian closure and then take some limits. So limits we have, but we can't construct these internal homes in E. So what we are going to do instead we're going, instead of enriching our category in E, we're going to enrich it in presheaves over E. So this notation, PSHE, this stands for set valued presheaves over E. And whenever I have two simplicial objects, I'm going to define a home presheaf from X to Y, which is a presheaf over E. And it looks like that. To each object E, it sends the set of all morphisms from X cross E into Y. And if you're looking at this notation, it might look a little bit confusing. I need to explain that we are using this indices in kind of opposite way to the standard convention. So whenever I put an index, a lower index on home, this index represents the category that my home objects are taking values in. While normally I would decorate it by the category that I'm drawing my objects from. The reason for this is that we are really interested in only one category, SE, but in our paper we have about 4 different types of homes in this category that take values in various things. So home set stands just for the set of morphisms in this category. Home PSHE stands for the presheaf of objects from X to Y. And this definition is set up in such a way that we have those presheafs. And if any such presheafs happens to be representable, then the representing object would be an honest home in the enrichment of SE in E if it existed. But as it stands, it does not always exist. It exists only occasionally. For example, if we home out of one of those representables underlined, then you can easily see that this amounts to evaluating my object at a given index. So this particular home exists, i.e. this home presheafs out of delta is representable. And then also because these things, the boundaries and the homes are finite colimits of representables, they are turned by this home factor into finite limits. So homes out of these things are also representable. And as it turns out, this is just enough of those enriched homes that exist in order to make sense of the small object argument. So somehow the theme here is that we put very weak assumption on our category, which gives us very few universal constructions to work with, but we are squeezing out some very special cases of these universal constructions that exist. So not all colimits exist, not all homes exist, but some of them do, and that's enough to do what we are to carry out the construction that we want to carry out. So keeping this in mind, let me elaborate on the small object argument and how we construct weak factorization systems out of that. So if I have two simplicial morphisms, I and P, I'm going to define the preshift enriched lifting property between those objects by saying that a map from the home presheaf of morphism from B to X to the presheaf of lifting problems between I and P has a section. So the presheaf of lifting problems is this pullback of home presheafs this is really the object of commutative squares that are the lifting problems connecting I to P. And what makes this lifting property enriched is that we are not just asking that solutions exist, but that we can pick those solutions via a presheaf map. And of course, what happens here is that if all home objects, if all home presheafs here happen to be representable by objects in E, then we can form this problem object as an object in E, and then in this case, asking for our presheaf enriched lifting property reduces to an E enriched lifting property. So we can instead formulate this in terms of this map having a section in the category E. All right. I hope this makes sense. I realize that I'm going fairly fast through this, but of course, again, feel free to ask if you need any clarification.
Yeah. Can I?
Sure.
Yeah. I actually don't understand the typing of the definition of hom PSHE when you go back a slide. Maybe you can go through this a little slower. So
Okay.
X, yeah. So X and Y are simplicial objects in E.
Yes.
E. E is an object in E.
Correct.
And then X times E and Y are supposed to be sets now.
So X times E. Okay, yeah. This is this notational confusion that I was trying to explain. X times E is again a simplicial object. I'm just level-wise crossing.
Yeah.
And Y is another simplicial object. This notation stands for the set of all morphisms of those simplicial objects. So
okay. Sorry.
The index stands for the target category of this home functor.
Yeah, so that was my confusion.
All these homes live in the category of simplicial objects, but this one takes values in sets, this one takes values in presheaves, and here, if you go, you see that, for example, this one takes values in E itself. So because we have one category but many different home functors, we choose to decorate them this way. Is it helpful?
Yes, very much. Thanks.
Okay, great. Okay, so let me clarify that, I mean, it's not so much a clarification, but a comment which might make sense to some of you who are used to doing some of these enriched factorization systems. Namely, the category E carries a factorization system where the left class is the complemented inclusions that we talked about, and the right class is split epimorphism, so morphism with a section. What we are doing here is we are somehow saying that our weak factorization systems that we are constructing in the category of simplicial objects are enriched with respect to this factorization system in E. In the sense that like appropriate pullback home or push-out product property would hold. Or at least they would be enriched in this way if our category was in the first place enriched in E. But it is not quite. That's why we are kind of going back and forth between presheaves and actual objects in E. Okay. So having said that, an enriched factorization system, enriched over presheaves, is just exactly what you expect. It is a pair of two classes of morphisms so that they determine each other via this presheaf enriched lifting properties, and then every morphism factors as expected. And a theorem which tells us how to construct these things is a slight variation on the standard small object argument. It has the following assumptions. So my set of generators I needs to be a countable set. All elements of this set, all morphisms, all generators are level-wise complemented. Morphisms between finite objects. And in this case, I can run a version of a small object argument and construct a factorization system where the right class are things with the right lifting property with respect to I, and the left class is, with a left lifting property with respect to L. So I think everything in this theorem has been formally introduced by now, except for finiteness. So this is a fairly specialized notion which has been chosen to fit into our context, and is perhaps a little stronger than what you think. I'm not going to go into the discussion of what finite means actually, but I'm just pointing out that there's something which requires more explanation that I'm able to give in this talk. But it turns out that, do I have more slides about this? No. So let me just make a comment about this theorem. The proof goes the same way as ordinary small object argument, except that in each step, when you attach solutions to a given lifting, to a given family of lifting problems along a push-out, what you do is that you don't take a coproduct of a bunch of these lifting problems. You really take a tensor indexed by an object of E, namely this object of lifting problems. And the finiteness assumption in particular implies that this problem of that this object of lifting problems exists as an object of E, i.e., the presheaf of lifting objects is actually representable. So somehow, in order to formulate the general definition, I need to speak about this pre-shift enriched lifting property. But in order to carry out the small object argument, I need to know that lifts against generators are actually representable. And this is what makes this work on one side. And the other ingredient that's necessary to make this work is the assumption that our generators are actually level-wise complemented. This is what helps us well, actually verifying that what we have obtained is a morphism in R. This goes back to this decidability, but since I didn't emphasize the logical aspect of this, I think I'm not going to elaborate on this very much. But this is closely this closely follows sort of the constructive version of the small object argument that we had in the previous paper. Okay, so with these definitions and with a theorem in hand that allows us to construct the two-weak factorization systems, we have the classes of cofibrations, trivial cofibrations, fibrations, and trivial fibrations, as you would expect. So cofibrations are generated by I, trivial cofibrations are generated by J, i.e. boundaries and horns, and then fibrations and trivial fibrations are complementary classes. And a lemma here, which explains the terminology from the very statement of the theorem, is that the factorization system corresponding to cofibrations and trivial fibrations is really nothing but a ready factorization system lifted from the factorization system of complemented inclusions and split epimorphisms in E. In other words, a morphism is a cofibration if and only if it is a really complemented inclusion. So these relative latching objects are complemented inclusions, and the trivial fibrations are exactly really split epimorphisms, i.e. these relative matching objects have sections. Again, I'm not going to elaborate on this very deeply, but if you are familiar with the Reedy theory, I think you can recognize how these things fit together. So this is what the terminology comes from, and back in the previous paper, when we had this constructive background, these were called really decidable inclusion, and then there was this logical interpretation to all these things, which I'm not going to go much into this. So there's a okay. So this way, I have explained what cofibrations are and what fibrations are. We still need to say at least a little bit about Rook equivalences. So there's a couple of ways of defining this. Here's like a relatively straightforward definition that we settled on. So first, we define a pointwise weak equivalence by evaluating, if I take any simplicial object and home out of an object of E, so this is just an object of E, not SE, I get a simplicial set, and here's yet another home with notation. This time it takes values in simplicial sets. So if I land in simplicial sets, I have a standard notion of weak homotopy equivalence available there, and I'm just saying that the pointwise weak equivalence is something that becomes a weak homotopy equivalence when homing out of all objects of E. And that turns out to be a correct notion for morphisms between fibrant objects, not in full generality, actually. In particular, we can show that a fibration between fibrant objects is trivial if and only if it is a pointwise weak equivalence, which is, of course, the main thing to prove when verifying existence of a model structure is that the trivial fibrations are exactly the intersection of fibrations and weak equivalences. So this is what happens for this naive class of pointwise weak equivalences, which are not quite weak equivalences yet. But in this case, this is obvious, or rather follows from the classical theorem on the calculated model structure. And then somehow the main difficulty in the theorem is to extend this to all objects, not just fibrant objects. And we simply define a weak and actually, yeah, I should have corrected this. I don't want to say weak homotopy equivalence here. I think I just want to say weak equivalence. I tend to reserve the name weak homotopy equivalence for actual simplicial maps of simplicial sets. In simplicial objects, I would really say weak equivalence. So consider this a typo. And I'm going to say that it is a weak equivalence if it has a canonical fibrant replacement that is a pointwise weak equivalence. And by canonical fibrant replacement, I mean something obtained from the small object argument by factoring the map out of initial object into a cofibration followed by a trivial fibration. And as I said, the proposition needs to be generalized to all objects in order to complete the proof of a theorem. So the actual proof is fairly long, and I'm going to touch only on one or two main points in this argument. And in fact, as I mentioned in the very beginning, our work is closely based on the two papers on the constructive model structure that we introduced previously, which has 3 different proofs in there. And in principle, any of these 3 different proofs could have been used to produce this generalization. We have decided just to settle on one so that we are not going to repeat all the same things again. And we have chosen the proof which is inspired, it is mainly contributed by Christian Sattler, and it is inspired by some developments in homotopy type theory, as you will recognize in some of in 2 of the following slides. So one of the central ideas is an equivalence extension property, which I'm just going to explain this briefly. I'm not going to draw a connection between the homotopy type theory. Those of you who know, you know. This is a property that says that whenever I have a pullback square, let's look at the slanted one, which is a pullback of a fibration along some cofibration, and I have chosen a homotopy equivalence with some other object over A, then I can extend this in such a way, I can sort of extend this equivalence to an equivalence between y and y0 and y1. So to produce this object in such a way that I have a weak equivalence here, so that this one is a pullback of this. So both the back square and the top slanted square become pullbacks as well. So, and this has homotopy type theoretic interpretations, and this proposition has a long history of being translated into various contexts, and it turns out that it holds also in our context here inside cofibrant simplicial objects in this category E. I should have mentioned one important consequence of slightly different definition of a cofibration is that most typically not all objects are cofibrant in this model structure, unlike in the classical case of simplicial sets. And that is what is the source of many difficulties in proving the theorem. And I will actually sweep most of those under the carpet because that gets very technical, but this is where a lot of difficulties actually lie. So the purpose of equivalence extension property is to prove fibration extension property, which is also something that has homotopy type theoretic interpretations that I'm not going to talk about. But what it says is essentially that whenever I have a fibration over some object and a trivial fibration to another object, then my original fibration is a pullback of some fibration over this larger object. So I can extend fibrations over trivial cofibrations. And because my I mean, so a corollary of this, which is I'm sweeping a lot under the carpet here, is that you can use this fibration extension property in a couple of related things that I'm not writing down to extend the statement that I previously gave about pointwise weak equivalences and fibrations that are pointwise weak equivalences to all fibrations, this time between cofibrant objects. And unfortunately, I need to point out another typo that I have on the slide. This should not include the word pointwise. The point of the corollary is that we are extending something that we showed about pointwise weak equivalences to all weak equivalences now. So a fibration between cofibrant objects is trivial if and only if it is a weak equivalence, in the sense it has a cofibrant replacement that is a pointwise weak equivalence. And So this is still not quite what we want to show, because we really need to show this without the assumption that this holds between cofibrillant objects. We want to show this for all objects. And that's the part that I'm going to skip, because at this point this gets really technical and the talk would get much too long if I wanted to get into this. But what I'm saying is that there are some relatively well-known techniques, both old and fairly new, that if you work hard, you can make sense of them inside of this fairly weak context of countably extensive categories. So I think I'm going to conclude the discussion of the model structure itself at this point, but because I do still have a couple minutes, I would like to tell you something about the properties of this model structure and of the resulting infinity category, which is something that we understand only partially so far, but it looks like there are some interesting things that might be uncovered about this. So here's one motivating observation. If you take a group G and take the category of G sets, then that's a grothendieck topos. In particular, it is a countably extensive category. You can look at simplicial objects, i.e. G equivalent simplicial sets. In that case, our model structure coincides with the so-called genuine equivalent model structure. So this is a model structure where equivalences are not just underlying weak equivalences. These are maps that become weak equivalences under taking fixed points under every subgroup of a group G. And that is the central object of study in equivalent homotopy theory. So I don't think that there is any deep connection to equivalent homotopy theory here. I just find it interesting that a non-trivial and well-known model structure actually comes out as a special case. And this observation is a starting point of a theorem which actually tells us something more interesting about wider class of examples here. So here's some temporary definition, some provisional definition. I'm not going to go very deeply into the explanation of how this differs from other contexts, because you could say some things about this, but in the interest of time, I'm just going to say an object is connected if homing out of this object preserves coproducts, and it is locally connected. A category is locally connected if everything is a coproduct of connected objects. And there are these von Kampen things, which for the purpose of this slide could have been completely omitted, because all coproducts are von Kampen in my context. There are reasons why it is written this way, which is maybe a little confusing. No matter, just think about connected, locally connected as you usually think about them in category theory. Then we have a version of Elmendorf's theorem, which is originally a theorem about this genuine equivalent model structure, which says that if we have a locally connected and completely extensive category, then the infinity category associated to our model structure is equivalent to the infinity category of simplicial presheaves over the subcategory of connected objects in my category E. So if we take for E G sets, then the connected objects are exactly the orbits, the transitive G sets. And what the classical Elmendorf theorem says is that this genuine equivalent model structure is equivalent to the projective model structure over this orbit category. So this is a vast generalization where instead of sets, we have some locally connected, completely extensive category, and instead of the category of orbits, we have the subcategory of connected objects. And here's a sketch of a proof, but I think I'm not going to really go through the sketch of this proof, because I still have 2 more slides that I would like to say something about. But I want to point out that one thing that you need to pay attention to in this context is that the subcategory of connected objects is not necessarily small. Is it something special about the category of G sets that the connected objects form an essentially small category, because there's only so many of these orbits. So whenever I'm talking about simplicial presheaves in this context, I actually mean small simplicial presheaves. And a small presheaf is a presheaf over passively large category, which is a small colimit of representables. And there is some theory of presheafs which has been extended from the standard theory of presheafs to this context, in particular in terms of factorization systems and model structures. In such categories, you can construct, for example, a projective model structure on simplicial presheafs under certain assumptions, which is cofibrantly generated, but we really have no set of generators. We have a class of generators, because if you think about projective model structures, generators are indexed essentially over the objects of the indexing category, which if it is large, then you have a class. But under some careful under some assumptions and with some careful analysis, you can carry out small logic argument even with a class. And then it turns out that under this restricted Yoneda embedding from our category into these presheafs over connected objects, our enriched factorization system corresponds pretty much exactly to what you get from this class cofibrantly generated model, class cofibrantly generated small object argument. Okay, I'm going to. This is just a comment that there is a paper that appeared very shortly after ours, which does something similar under slightly stronger assumptions. But I'm not going to say much about this because, frankly, we haven't understood the connection yet. But I wanted to say that it is there. Then some other connections with some other properties of the infinity category are that the associated infinity category satisfy kappa descent as long as our category was kappa lextensive, meaning the homotopy colimits or the colimits in the associated infinity category also satisfy descent. And this time, not just coproducts, but all colimits, even push-outs, homotopy push-outs, homotopy quotients, and so on. So because it turns out that this entire process actually adjoins infinity colimits. I mean, this follows from the existence of a model structure, but there are also von Kampen. So somehow, short of being presentable, and this infinity category is rarely presentable, this is some sort of infinity topos. It's not quite infinity topos, but it is close to being an infinity topos. And then also, if original category was locally Cartesian closed, this one is as well. Like, I mean, in terms of elementary infinity toposes, like I don't think that we are completely settled on how the theory should work, but people are investigating this. Okay, so John, how should I stop here or
well, you could go on for another 5 minutes if you like.
5 minutes? Okay.
Yeah.
I think.
What do you think?
In 5 minutes, I can. Are we?
Hello.
Hello. I mean, you're breaking up a little bit for me.
Sorry. Yeah. Sorry. Would you like 5 minutes more? Or?
I can speak for 5 more minutes if that's not inconvenient.
That's great. Yeah. That's great.
Okay. I mean, I just have 2 slides left, and what I'm going to say in the final few slides is one theorem which generalizes the previous one, and then some conjectures and speculations that I don't even understand very well, so I just want to throw them out. So now let's say that we have a category which is either countably complete or countably extensive. So, for the purpose of this, because I have only a few minutes left, let's disregard countably complete. Let's just say that we're countably extensive. It turns out that we can kind of go even a little bit beyond extensive categories with this theorem for the reasons that I'm going to skip. So just think, let's say that it is countably extensive. So compared to the previous thing, we're dropping the assumption of local connectedness, and now we are saying that the homotopy category, the infinity category of SE, here I'm writing fibrant objects for a reason that I'm going to also omit explanation of. This infinity category embeds fully faithfully into simplicial presheafs over E. And there's a characterization of which objects are in the essential limit. These are homotopical limits or geometric realizations of Kahn complexes in E. So I'm not going to explain this completely. Here's a sketch of a proof. I don't think that I want to go through this, but essentially what I'm going to say is that let's concentrate on this thing here. We take simplicial objects and embed them into simplicial objects in the category of families in E. This category is a free coproduct completion of my category. It is a lextensive category and it is locally connected. Indeed, if you unravel the construction of this, the connected objects in this category are exactly my original category. Because these things are essentially formal coproducts of things in E. So I can apply the previous theorem, the theorem about this, what we call Elmendorf's theorem, to this category because it is now locally connected and countably extensive, or even completely extensive. And then we can prove this theorem sort of by observing that my category embeds into this category. And the other things are a bit of an explanation of how this works, but this is maybe what I don't want to go into because this would require a little bit of commentary about semi-simplicial objects and a couple of things that go complicated here. But well, it turns out that I can. So I know that I'm going very quickly through this, but I'm doing this only in order to get to my final slide. Like the takeaway from this theorem is that I can embed my infinity category into the infinity category of presheaves. And there is a particular characterization of the essential image of this embedding. And if you look at this, you can recognize some connections to some classical category theory. Namely, under the same assumptions as the previous theorem, the full subcategory of set truncated objects, so this is truncation, I mean, in terms of higher topos theory or homotopy type theory, if you know what this means, in the homotopy category is equivalent to the X-lex completion of E. So if you think of E as a category with finite limits, you can find a universal exact category into which this embeds. And an exact category is essentially a category with finite limits and von Kampen quotients under equivalence relations. It's just briefly speaking what it is. And there is this very well-known and classical X-lex completion. It turns out to live as a nice subcategory in our homotopy category. And therefore, we conjecture that our entire construction is somehow related to an infinite categorical version of that. So the conjecture that we make is that if we introduce appropriately what an exact infinity category is and what an infinity categorical X-lex completion is, then our infinity category is not quite this exact completion, but it contains it as the subcategory of finitely truncated objects. And I have to say that I don't entirely understand what's going on here. I mean, it is a conjecture, so we don't know the proof of this, but this was really conjecture formulated by Simon Henry, and he has more insight into what this exactly means and why it should work this way than myself. But I think that my final point here is that we can recognize analogs of some very classical category theory, high categorical analogs emerging from this work, which sounds like something that we might want to investigate, but we don't really understand this very well yet. It's also almost 1:05. This is my final slide. There's one more conjecture here, but it referred to something that I skipped before, so I'm not going to talk about this. It is just a mild variation of this one. So yes, I'm going to stop here. Thank you very much for your attention.
Okay, thanks very much, Karol. We have a usual sort of silent round of applause. So that was an excellent talk. Yeah. So if anyone has a question, you're welcome to mute yourselves.
Of course, feel free to ask if you have any questions. Yeah, I do realize that this was quite fast and low on details, but if you want me to elaborate on anything, no problem.
Yeah, maybe just a general question. What was your initial motivation to look at these classes of categories and the corresponding construction? Was it just to push that notion of Khan?
So the story went more or less like this. As I said, we had this constructive model structure, and when you have a theorem like this, well, and you are thinking about categorical models of such theories, then you think, well, this should internalize into Grothendieck toposes. And I have to say that initially, in our group of collaborators, there was a little bit of disagreement about how obvious it is that our constructive theorem immediately yields these model structures in something like Grothendieck topos. And I mean, so some people thought that it was relatively easy. Some people thought that it was harder. I'm not a logician, so to me it did seem hard. But it is just my perspective. So we decided. But we decided, okay, let's take a look into this, and maybe let's try to write down the argument categorically, rather than just saying, "Oh, let's do all of this in the internal language of the Grothendieck topos." And at this point, we really thought that Grothendieck topos is more or less what is needed. But when we started going into the argument, well, we were noticing that certain types of that the kinds of arguments that we were carrying out really didn't use the full strength of a Grothendieck topos, and we didn't need presentability, we didn't need quotients, and so on. And after a while, it turned out that we can land on countably extensive categories. So if this was certainly not something that was an assumption that this is a nice class of categories that we want to work with, it's just something that we ended up with by shaving off more and more of original hypothesis. And at this point, I should say as well that it should be possible to go further than countably extensive categories. Namely, it should be possible to do something like finitely extensive categories with some sort of internal natural numbers object, perhaps some sort of parametrized natural numbers objects, like list objects or something of the sort, where so the point is that and that would in particular include things like elementary infinity toposes with natural numbers objects and things like that. The reason why we didn't go that far was that, well, the fact that we have countable colimits at our disposal here makes it possible to carry out all sorts of infinite constructions sort of externally to our category. But if we insisted on having no infinite colimits and our only source of infinity would be this internal natural numbers object, then all sorts of combinatorics of the category delta, that is an infinite category, would have to be internalized in this very weak context of finitely extensive categories, which just seemed like an overwhelming thing to do. Whether this is worthwhile is kind of up in the air, but it seems that it is possible to go even further, and that will be even more kind of logically appropriate because countably extensive category are not quite elementary because of these infinite colimits. Yeah.
Yeah, thanks. Yeah, that's an interesting direction to go with the elementary infinity toposes, and maybe then, right, it would be then an interesting question if they can represent elementary infinity toposes in some sense.
Well, yeah, I will agree with you that that's interesting, but I don't have much in the way of speculation about how it would really play out.
And this conjecture here, and generally these musings about effectivity basically popped out in the end. Then that.
So the conjectures in terms of excellence, completion, and so on, they sort of popped out. I mean, so the point is that if you look at some of the constructions of X-lex completion that are like sort of proof relevant equivalence relations in category E. Those sort of look like the beginning of a simplicial object in E, if you look at it through the right way. And so it was kind of a natural thing to look at, but it's not entirely obvious that it turns out this way. Like when it comes to effectiveness, I have to say that I am myself partially confused about this because in the end, I have to admit my ignorance. I still don't quite understand what the word effective means. Like, because there's a number of notions that have the word effective in them, and I think that the common theme behind all of them is kind of elusive, and we were a little bit hesitant in whether we should use the word effective in order to refer to this model structure. In the end, we did use it, but I wouldn't put too much weight into these connections. There are certainly some, but I myself don't feel confident enough to say something very specific about that.
Yeah, thanks.
Yeah, no problem.
Perhaps just one small question. So it seems quite surprising that you you only require co-products.
Mm-hmm.
Do you have any examples without, say, co-equalizers, where the theorem is interesting, or do you have any examples in mind that don't have?
So we don't have like, I mean, we haven't really investigated any examples very specifically, but I believe that a lot of those, I mean, not all of them, but a lot of those co-product completions will fail to have more co-limits than co-products, right?
Mm-hmm.
So while we haven't studied any of these examples really, I think that you could find some interesting things that fail to be co-complete among those co-product completions, I suppose.
Okay, and just on the same theme, do you really need finite limits as opposed to, say, products and some special pullbacks or something?
So I mean, yeah, that is an interesting question. I don't want to say for sure, but I think we pretty much need arbitrary finite limits. And I flip back to the slide where I think you can kind of explain why. Because in order to run the small object argument, you may recall I said that you need certain home objects to be represented, to live in E. And how we construct them is via finite limits. Namely, a home object out of representable always exists, and this doesn't require any limits. That's just evaluation, right? At this particular level. However, we also need home objects out of these domains of the generators to be representable. Mm-hmm. And because those are finite colimits of representables, when you home out, they turn to finite limits of those things. And those limits look pretty arbitrary to me. I haven't really looked, but it seems that I wouldn't be able to get away with a smaller class of limits. So yeah, all finite limits actually seem essential.
Okay, thanks. Any more questions?
Maybe for that small object argument, is there a general enriched version of the small object argument, or which for some reason didn't apply here, and therefore you had to do your own version, or isn't?
So there are, I mean, we haven't invented enriched factorization system or enriched small object argument. These things certainly have been studied before. There are papers by Real, for example, that investigate these things, and some versions of small object argument, or of the enriched small object argument have existed before. They were not suitable for our purposes for reasons that I can't quite explain in the context of everything that I've said in this talk. But essentially, it is somehow maybe let me put it like this: the enriched small object argument that we have here, it really arose as a variation of a constructive small object argument that we had in our previous paper. And in the constructive small object argument, this level-wise decidability played a particular role. Namely, the point is that, okay, I'm going to say something about this constructive small object argument. Namely, when you sort of run your small object argument, you obtain a map that you'd like to now show that it is a vibration. What you do, you take a lifting problem and you say, okay, the domain of my map was obtained as this colimit from in the course of a small object argument. I need to say it factors through some stage, and then at this stage I go one step further and I find my solution. Constructively, the problem with this is that, of course, whenever constructively you prove a statement of a form, there exists something, then you are obliged to actually produce that thing. So in particular, whenever you say my lifting problem factors through some stage, you have to identify this stage. And constructively, the problem with that is that, of course, you could say something like, let's take the minimal number k such that my map factors through the kth stage. The problem is that constructively, not every inhabited set of natural numbers has a minimal element. The decidable ones do. So therefore, you need some notion of decidability in order to carry out this small object argument. In our context, I should say that the entire meta theory in our current work is classical. We didn't bother to do all of this constructively, although probably it could be. That's like a separate thing. But the point is that our version of small object argument depends on these assumptions of level-wise complemented inclusions, and this is the only innovation that we introduced into this. Other than that, other than the observation that this is the assumption that makes everything work, everything here is very, very standard and classical. And I said something about sort of logical origins of this condition, and I think that will have to suffice because I can't really elaborate on this too much in the context of this talk. But yeah, that's so to summarize, it is a new version of a small object argument, but it differs only very slightly from the ones that were known already.
Maybe I just mentioned that it sounds like what you're calling this constructive small object argument, if it involves sort of adding fillers only for maps which you haven't already factored through some earlier stage, that's also a special case of the algebraic small object argument.
Yes, but
if your classes of maps are all monomorphisms.
But in this small object argument, we actually do not. I mean, we attach everything. We do not skip things that were.
Okay.
So this is, there's very little. I mean, this really most closely resembles the very standard classical object argument in the sense of Equivalence.
Okay.
It's really the differences in this level-wise complemented inclusions.
Okay.
So in particular, we don't worry about duplicates and stuff like that. I mean, of course, if you think about this constructively, the way the argument goes, some of those attached solutions will be distinguished as preferred ones because we kind of think about vibrations as being structured, but you don't worry if we have more of them.
Okay, thanks. Perhaps if nobody has an urgent question, perhaps we can end it there and thank Karol again for.
Very well. Thank you very much again.
Yeah, and so that's it for today. And then next week we have a model theory talk from Jonathan Kirby. So that's next week. And yes, so we can stop recording.